Our session on the compiler and program verification CPP, and our first speaker is Lasse Hansen, and to present the last yard foundational end-to-end verification high-speed cryptography.
Thank you. Okay, when you want to implement cryptographic protocols, you often run into these problems. So first off, there's a specification gap, and secondly, there's an implementation gap. The specification gap is whenever you want to implement something, the standards are usually written in informal pseudocode, which makes it hard to know exactly what the details are of the implementations and what exactly you want, which are protocols and what you actually want to implement. Next up, there is the implementation gap. So whenever you want to actually implement something, you can either write it in some language where you then compile it. However, then you just have to trust that your compiler does the right thing. And this is a problem when you have unverified and unoptimized compilers. Furthermore, because implementations in cryptographic protocols are very important that they're actually efficient, most cryptographic primitives are often implemented directly in assembly. And this can cause that you actually have a loss of abstraction and introduce more complexity, which makes it harder to actually understand what's going on and can introduce bugs. So to prevent this, we'll want a unified foundational framework for end-to-end formal verification of efficient cryptographic implementation. Thus, we have made this paper, the last yard foundational end-to-end verification of high-speed cryptography. I'll start by introducing some of the elements of our framework. So first off, there's HEXPEC. HEXPEC is a high-assurance specification language. It provides a shared language between cryptographers, programmers, and proof engineers. It makes the internet standards such as IETF and NIST machine readable, which means that you can actually run your standards and actually check if your implementations does the correct thing by running them against the standards. So HEXPEC also is a simple subset of Rust, so many cryptographers and people who actually implement these cryptographic primitives are familiar with the language of Rust, since it gives some guarantees and has efficient translations. And the HEXPEC language has translations to proof assistants such as COC, EasyCrypt, and F***, and more backends are being developed, and more tooling is also being developed to support the HEXPEC language. So for what we're actually using HEXPEC for in our work, we take the standards that we then produce HEXPEC code for, and then we generate these following artifacts. So we generate a functional specification where it's easier to define and prove properties about the specification. We define an imperative SS-proof specification, or we translate to an imperative SS-proof specification, which is closer to efficient implementations, which makes it easier to show equality to our implementations. And lastly, we add some translation validation for this translation, where we build a proof of equality between the functional specification and the SS-proof specification. So what this looks like in a workflow is that we take a standard, write in HEXPEC, and then we translate that specification automatically to SS-proof specification and a functional specification and a proof of equivalence between them. So for SS-proof, this looks like okay, so what happened? Sorry. Yes. Okay, for SS-proof, this what we actually use is SS-proof, this language, which is a foundational framework for modular cryptographic proofs in COC, which essentially embeds a stateful language inside of COC. And the Dijkstra monad framework gives us a program logic to reason about this embedded language, so we can actually show properties about things implemented in SS-proof. Specifically, we can show security properties. So what we're actually using SS-proof for in this work is we use it to show the equivalence between an implementation and a specification, and we use it to show security proofs about the specifications. So back to HEXPEC. So for HEXPEC, we have this automatic translation And what we actually do for this automatic translation is we have a modular syntactic translation where we define it as triples. So we have this triple with the functional specification, this proof specification, and a proof equality. And this can also be seen as a binary logical relation. And an example of such is this lead binding. So if we have a lead binding in hexspec, which is more or less just Rust, we have lead x, by in k, then that becomes translated to the functional coq code. It becomes just a lead binding in coq, so lead x, by, and k in coq. And for SS proof, it then becomes a actual binding, so a monadic binding. So we bind y to x in k. And then the proof of equality between them is just the equality or the proof given in SS proof for these bindings. And we can then build other triples like this for other constructs like loops, mutable lead bindings, early returns, operator calls, lifting of pure values, and so on. And then combining all of these elements, we can then build the entirety of the translation, and this is then done automatically. So when we have the translation, we end up with this triple for the entirety of the translation. Now for Jasmine. So Jasmine is a low-level language designed for implementing high-speed cryptography. It has a compiler implemented and verified in coq, supporting both x86 and ARM, and it has a formal big-step operational semantics in coq. Jasmine is also an imperative language with structured control flow like loops, conditionals, and procedure calls, and it has types for booleans, integers, and bit words of various sizes and arrays. And the compiler for Jasmine produces predictable assembly code. And this is important as we can optimize the code, and we can make sure that we're not introducing bugs whenever we are compiling something. For what we actually do in this work, we take the existing compilation to assembly, and then we hook into that, and we do a de-extraction by pretty printing the internal AST into coq syntax. We then take this AST and translate it to SS proof. And this translation, for this translation, we also get a mechanized proof that the semantics are preserved. And the translation is also done automatically. The main theorem for this statement about the operational semantics being preserved is for function calls. So if you have a function from some arguments to a result value, then translating the function on some arguments also returns the translation of the results. So it's doing what you would expect. If you translate all the elements, then they still line up. But further than that, we also have that the translation modifies memory in an equivalent manner. So we can actually combine that with the correctness theorem, the existing correctness theorem with the Jasmine compiler, to allow us to prove properties about Jasmine in SS proof, and then transfer those proofs to the assembly code and be sure that we actually get the properties about the memory that we want. So if we try to add this to a workflow, it looks like this. So we have the Jasmine implementation that then gets translated to this Jasmine coq AST, which can then be translated to assembly, which was the pre-existing work in Jasmine. We then add this translation to SS proof, and then you can by hand add an equivalence proof between this SS proof implementation and an SS proof specification. And lastly, you can also add security proofs for these implementations. Yes. Now, I'll show the workflow on an example, and the example will be this one-time pattern. So if we have a hexspec definition, which is more or less just Rust here, we have some mutable bindings. So we take two inputs, store them in some memory locations, then take the XOR between them, and store that in memory location and return that. Here we're using memory locations just to illustrate how memory is handled by the translations. We then automatically translate this. This translation is then giving us these triple constructs, where we have the lead binding, which is the mutable lead binding here, on some location. So we actually automatically get the locations translated, and all of these triples allows us to have both the functional specification and the SS-proof specification by this statement, and the proof of equality between the two. Now for the Jasmine implementation, we define some XOR by taking two input values. Then we make a temporary register where we store the first, XOR it with the second, and then return that. This we then again translate to SS-proof. Here it then becomes put statements where we store the values, and then XOR operation, and then a get statement to actually get the result out, and then we return that. Lastly, we then show the equivalence between the specification and the implementation, and this is done in the relational program logic of SS-proof. Here we can see that we're actually just looking at the return values being equal by value. So you just step through the code by these logical relations until you get that the two values agree for the return. Now for some security properties, we first want to define a couple of definitions. So in SS-proof, we define a package as a collection of procedures with imports and export interface. A game is then a package without any imports, so you can actually run all the exports. A game pair is then two games with the same exports, so you can look at whether these two are equal. The idea is then if you can show, for example, the equality between a real encryption scheme and an oracle, then you can say that you can swap one for the other. And if you can't distinguish these two, then that means that you have some security. We then also use this game hopping, which is where you chain these pairs of games to get an equality all the way, so you can just connect from one end to the other and still have the security properties you want. So if you have one pair of security, and which has the actual security properties you want, you can just connect to either end of that whenever you want to extend it. Yes, so let's look at how that actually looks. So a Jasmine game here is a function, so this is the only export it has, which is this one-time pad. So it takes a key, which is sampled uniformly at random, and then it XORs that key with the message for the Jasmine XOR. We then look at the SS-proof implementation. So for the SS-proof implementation, we have, again, we sample a key uniformly random, but then we do the XOR operation with the mathematical XOR operation. We already have a proof that this one-time pad for SS-proof is secure because it's equal to an idealized implementation. So if we can just show equality to the actual implementation here, then we get the security properties we want for the Jasmine implementation. So that's what we do. We combine the first equality with the second equality, and then we get NCPA security for the combination. So that's what we're using these game hopping to actually accomplish. Yes. So now I showed that we actually have a framework for doing specification and implementation from end to end, fully verified. So what we actually do in this is we start by specifying a hack spec, implementing a Jasmine, then we de-extract the Jasmine and translate automatically both hack spec and Jasmine into SS-proof, then we prove equalities, and then finally we show security properties in SS-proof for this. So now let's try and evaluate our framework on a larger example. So we'll look at the advanced encryption standard as an example. So for this, we are looking at a pseudo-random function encryption scheme. So here, the pseudo-random function is a function which takes two arguments, some message and some key, and then it produces random-looking output. This encryption function will then be that we take the pseudo-random function and run it with some randomness, we sample uniformly, and a key. And then we use that for padding of the message. So we basically do one-time pad again, but using the pseudo-random function. Yes. And the way we actually wanted to show security for this is we start by making an intermediate implementation in SS-proof of this scheme. And then we have the existing scheme, which is the functional implementation in COG. And then we want to show equality between the functional and imperative implementation, and then the imperative implementation and the translated Jasmine code. And then finally, by doing that, we connect it to the existing security proofs. So what the encryption function actually looks like in Jasmine is this for AES. So we actually take AES and run it on some values, which gives us a mask. We then take that mask and XOR it with the message, and that gives us the cipher. If we hook that encryption function, so first we translate it to Jasmine and hook it into this security game where we generate a key, then sample uniformly at random some value, and then do the encryption. Then we get the scheme displayed before. We can now prove this is indistinguishable from the scheme where we just do some cleanup. And finally, we can show equality from that to the actual real implementation of AES in SS proof, which was a pre-existing work. So by combining these two, we can again show that we can go from adjustment, translated adjustment, to actual real SS proof specification security proof. And we then also combine that with an equivalence to hexspec. So we define a AES implementation for hexspec and show it equal to that. So in that way, we get a framework or we get a translation from a specification all the way to assembly with the security properties in the middle. And because of the way that the Jasmine translation works, we also get the security properties actually translate down to the assembly. Yes. So in conclusion, what we have done is contribute a framework for end-to-end verification, and we have made a monadic embedding of a simple subset of Rust into SS proof with a refinement relation to a logical specification in COG. We've done pretty printing of Jasmine and then automatic translation to SS proof. And the framework we've done has strong guarantees. For hexspec, we have the translation validation, which says that the functional specification is equal to the imperative specification. For SS proof, we do the equivalence proofs and security properties, showing that the implementation and the specification are equal, and we actually get the security guarantees we want. And for Jasmine, we've shown the preservation of operational semantics and robust compilation, which already exists from the pre-existing work on the Jasmine compiler. But we reuse it here to get robust compilation with this translation. Thank you.
Thank you. We have time for many time for questions. Use the microphone, please. There's a microphone there. Thank you.
Hello. Thank you for the presentation. How do you feel your work compares to, for example, what has been done in F-star, for example, HACL, in terms of cryptographic verification?
Part of this work is getting the entire end-to-end verification. So we're actually connecting it with a specification all the way down to the implementation. So we are adding, the pipeline is now fully connected instead of just being from the specification, or just from the implementation up to security properties, about a single implementation.
Please introduce yourself.
Hello, Adam Chapala from MIT. My question is mostly probably about SS proof and not your new work per se, but you showed us examples using an equivalence relation, connecting versions or steps in a game. Wondering more about what that relation is. In computational models of cryptography, wouldn't we normally have some sort of quantitative degree of similarity there, whereas there are symbolic models that avoid that part, but they're kind of approximating in ways that can allow some security issues to come through. So what relation is that actually?
So what we're showing here is equality of the distributions. However, we are not really using much sampling of randomness here, but in the steps where there is actually randomness, what we show is that the two are equal with respect to probability distributions.
Doesn't that almost never hold for real protocols? There's always some amount of loss of fidelity.
Well, up to some, yeah. So.
But if you have a fixed additive approximation factor, then you don't have transitivity of the relation anymore. So something has to be going on here that's more complicated than we would think from the slides.
This is very similar in power to EasyCrypt.
Yeah.
Not in terms of automation, but in terms of the logic.
Does EasyCrypt have numbers on the steps or not?
There's an extension to it that can, and we could do the same. But they've done a lot on perfect security, where you can actually do this.
Got it. Thank you.
Thank you, Jan de Mount Hughes, University of Strathclyde. I think that was a very interesting talk, and I'm more concerned about the potential impact. And you say you want to make RFCs machine checkable in a way. You said machine readable because there's a slight difference there for me. Have you thought about liaising with the RFC community and saying, like, what needs to be done to get your solution adopted? Because I know they're quite restrictive and quite conservative about changes to the RFC standard.
So there is some work in actually getting some of these things into RFC standards. I think there is one of the protocols that have actually been formalized.
Hashing to curve.
Yeah.
Yeah.
So they're actually somewhat acceptable of doing this.
Oh, cool. Thank you.
Hexpack comes out of the Hex community, so that's a community that precisely tries to bring them together.
Thank you.
So they're very receptive.
Thank you.
Any more questions? I have a question. It wasn't entirely clear for me the functional specification role in your overall picture.
Yes, so we have not used the functional specification a lot for this because we already had some pre-existing work that was easier to connect to. But you could expect that the functional specification is a lot easier to prove some properties about. So the idea here was that you can connect the framework entirely up to the functional specification, and then you can show things that are easy for the functional specification on that side and things for the empirical specification on the SS proof side. So you have both both sides to actually do the.
But now it's not integral part of the proof harness,
So it's not integral for this, but you could imagine, for example, the last AS example where we show that some functional implementation is equal to some imperative implementation, and then to the translation, you could imagine just using the entire framework to get to the functional specification. The reason we didn't do that here was that we had some pre-existing functional specification we could reuse.
Okay. Okay, if there is no more questions, I guess we can let's thank the speaker one more time.